Okay, so I've been going over the final exam review. Sorry, I don't know what's happening in my brain. And I was just going based on my notebook, but I did realize I have this old iPad. It's like an iPad mini 2 or something crazy like that. But so that you can kind of see the questions if you don't have access to them already. And I believe, so I've answered all these questions already, but the question I'm on now was question 18. So how many chiral centers are there in this drug? So what I usually do on a problem like this, and I still am going to just write it out just so you can kind of see how I would approach this. So it looks like this. So there's wedges and dashes drawn in actually to make this a little bit easier. There's 2 hydrogens here, 2 hydrogens here. There's already 4 bonds to carbon there, so we don't need to worry about that. There's 2 hydrogens here, 2 hydrogens here, 2 implied hydrogens here, 2 implied hydrogens here. So there's only 4 possible chiral centers, 1, 2, 3, and 4. Now, sometimes I'll put these wedges and dashes to kind of trick you. So I like to check and make sure that there's none that are the same at all anywhere. And so I actually would look through and say, right here, we have an implied hydrogen. Oh, this actually might be a chiral center. I'll go back and look at that. Right here, we have an implied hydrogen. So there are 1, 2 CH2 groups. So are those 2 different? Because you need 4 different things attached. This is CH2, this is CH2, this is CH3, and this, as we keep going, is a carbon. So I'm going to actually say that this is a chiral center because we have CH3 on one side, CH3, and then the ring would go on that side, H. And then on this side, we have C, and then CH2, I guess, followed by C, and then a whole long spaghetti chain of all these things bonded. So that's one chiral center right there. Another one I'm going to look at right here is going to be very similar. You have CH3 on one side right here. There's an implied hydrogen, so that's at least 2 different things. And then going around the ring, these are obviously different because one side is CH2, and then CH3, and then it would go on down the ring. And then this, on this side, you would have CH2 followed by this carbon with 4 carbons bonded to it. So I would say that those are different. So both this and this are a chiral center because they each have 4 different things attached to them, and there's no plane of symmetry. Even if you drew a line right here down the middle, this one is going down into the plane of page, and this is coming out of the plane of the page. There's no plane of symmetry there whatsoever. Okay, and then I'm going to look here as well. There's a CH3 here, a hydrogen. CH2, that's the same, and then you have this carbon with all the stuff attached to it, and over here you have a carbon with 2 CH3s attached to it. So I'll say this is a chiral center as well. And then right here, they show the wedge and dash, but I actually think that that is to trick you because those are both methyl groups. So that means 2 of the same thing is attached right there. So that's not a chiral center. So we found 3 chiral centers so far. However, I think this could be one. So the first initial point is they all have CH2s. I'm actually going to redraw it and see if I can't make it a little bit easier to follow. This is a dash and this is a wedge. So definitely there's 2 different things attached on this side, because if you go around the ring, at some point you'll get to this where there's one CH2, one methyl group, and over here there's two methyl groups. So this is definitely two different groups attached. On this side, however, the only difference is the wedge and dash here, so I'm not 100% sure. Let me think about this for a second. My instinct is to say that because one of these is a wedge and one of these is a dash, that it would be a chiral center, but it would be difficult to assign an R and S value because it's obviously there's no plane of symmetry, which is what determines a chiral center, right? So I would say this is a stereogenic center, but I don't think you could assign R and S to it. So that's, I guess, kind of complicated, but so I'll accept on the answer key 3 or 4 if you knew that this wasn't a chiral center, if you spotted the correct chiral center. So I'll check your work on that and see who got that one right, because I would say it's 3 true chiral centers with one it's more like a stereogenic center. So I guess 3 is really what I'm looking for here. Okay, so then the next question is, what is the major product of the following reaction? So this is similar to one that you had on an exam recently. But instead of giving sites of product where you have to find out the E and Z configuration, it gives Hoffman product. So this reacts with tert-butyl alcohol and tert-butoxide. So when I see that, I am immediately thinking this tert-butoxide makes me think it goes to either SN2 and E2. There's a good leaving group here with the chlorine. So we have a nucleophile and a leaving group. That's how I know it's substitution or elimination. It's 2, so SN2 or E2. It's a secondary leaving group. So again, I think it could go either way, but because there is a bulky nucleophile, I think it favors E2 over SN2. So I would think you'd get the major product of the SN2, the major product of an E2, and not only an E2, but a Hoffman product for the E2. You don't have to worry about stereochemistry because these are all hydrogens right here, right? So your nucleophile can come and take one of those hydrogens and fill it in, and the stereochemistry will be good. And this is what your answer looks like. For some reason, I think it must be on the next page. So that would be answer choice E. I've seen questions like this before, where it'll have the right answer but flipped over. So this will have a dash and the double bond will be on the wrong side. So you definitely have to look out for that as an option. Okay, which nucleophile would be the least effective in an SN2 reaction? So the most effective nucleophile in an SN2 reaction would be one that is negatively charged. All these are negatively charged and they all have the same atom that is attacking the same nucleophilic atom. Oh, I realized I didn't update my answer key. 18 would be B or C, depending. 19 is answer choice E. Okay, so the best one for an SN2 reaction is going to be negative. All these are negative. So then the next thing you're going to look at is which one can most effectively attack and kick something out at the same time. And that's going to be the most narrow one, which would be the least branched one. So the best one, the most narrow one in an aprotic solvent, especially, we're assuming, would be B, because it's least branched, and so it's easiest to get in and attack and then do the backside attack and kick the other thing out. Why would HBr be a poor reagent for the dehydration of an alcohol? So this is kind of an interesting question. I liked it because it was a little bit different. And so I'm going to draw out the dehydration of an alcohol. So typically what we see in dehydrations of alcohols, it depends on if it's primary or secondary, if it's going to go by E2 or SN2, but we have an alcohol and then it gets protonated. So that's basically just an acid-base reaction, OH2 plus. Since it's secondary, it's going to go by E1, so the leaving group will leave. You'll get a carbocation, and then assuming that this alcohol is dissolved in water, the water will attack, and you'll end up with oh wait. I just added that alcohol right back. I mean, I guess all these reactions are reversible. This is why I shouldn't do these videos late at night when I'm tired. This is acid catalyzed dehydration. So your water, your nucleophile is going to take a hydrogen instead, and I actually think it would take this hydrogen. So ignore this one. This will fill in, and you'll get a double bond. So you'll get, that's how acid catalyzed dehydration works. So this question is asking, why would HBr be a poor reagent to do that? In my initial thought, before I read any of the answer choices here, is that Br minus is not going to be as good about stealing a hydrogen and filling this in, because HBr isn't that stable. This is a strong acid, so it disassociates to H plus and Br minus pretty easily, especially in water. So that's my thought, is Br minus isn't a very good base, and it might just even want to attack. So my answer choices are HBr is too weakly acidic to protonate the alcohol. I don't think that's true. It's a strong acid, so you can eliminate that. Answer choice B, the conjugate base Br minus is a good nucleophile and would attack the carbocation to form an alkyl bromide. I think that's definitely a possibility, so I'll put B as a maybe. C, HBr is strongly acidic, so the water molecule would not be a good leaving group after protonation. That doesn't make sense, because if water is protonated, then it is a good leaving group. So C can't be the right answer. And then D, HBr would be more likely to promote rearrangement of the carbocation intermediate. That doesn't really make sense either. We haven't heard at all about solvents or acids promoting rearrangement. We've heard about solvents helping the carbocation form in the first place, but not really about promoting rearrangement. So, and unless there was like a specific thing that it would rearrange, that's not even really the question. So my answer choice is going to be B, because I do think rather than steal a hydrogen and become HBr, which is relatively acidic, this bromine would rather just come in and fill in that carbocation with its excess electrons. It's much more negatively charged and reactive than water, and you would get a bromine forming. So this one's kind of a different type of question, because it's not really asking you like, work a problem, do something that you've already done before, repeat the steps. It's asking you really to reason your way through why this might happen, instead of just giving you like a sort of thing that you've seen before. And that is something I want you guys to really work on, is those problem solving skills. Okay, 22, what is the major product of the following reaction? So we add this double bond, and it looks like this is oxymercuration, demercuration. The first step, oxymercuration, the second step, demercuration. So you can go through the whole process if you want. Usually, if it's multiple choice, I sort of go through like a sort of shortcut, honestly, where I do it and then I don't draw out every single individual step. I draw the carbocation and the HGOAC and draw it donating its electron density, and then I know that that's where the alcohol will add. One thing I always do with these is I try to check to make sure that this is water and not another solvent, because water is what attacks right here, right? So you'll have OH2 plus initially form and the HGOAC here. And originally that adds anti, where this is a wedge and this is a dash. But because of the radical mechanism, which now you know radicals are sp2 hybridized, so they'll mess things up, it is no longer that stereochemistry. This also gets deprotonated, but I'm trying to go kind of quick for you. So the HGOAC gets turned into a hydrogen. So basically your final answer is this. And you also have a racemic mixture because of the anti-addition. It can go from either side. So The answer choice for that is answer choice C. I don't know why there's randomly an A down there. I wonder if I deleted another question. Okay, so the answer for this one is C. Except I would say it's that one plus it's an enantiomer because it adds Markovnikov, just like the carbocation goes there. That's where the nucleophile adds in, and it can go either way. So I don't really know why they don't put the plus enantiomer on that one, but you would also. Oh, I know why they wouldn't put the plus enantiomer. Do you guys know? Maybe? I just realized out of nowhere, it's because there's a plane of symmetry that cuts right in the middle. So this one sort of actually, if it's a wedge, it's coming towards us, and that's a dash, it's going away from us. So it can cut right through. There's a plane of symmetry. So there is no enantiomer because this is not a chiral molecule. There you go. Okay, so the answer to that one would be answer choice C. I'm just updating my answer key as we go. Okay, and then the next question is determine which side of the reaction is favored. So really on this one, this is an acid-base question, and I have a whole video. This would be the proper arrows on here, where I talk about how you do this. But basically, I compare the acids and the conjugate acid. So this is the acid, and you know it's the acid because on this side of the arrow it's protonated, and over here it's deprotonated, right? Because this Na is basically just a counterion. That means that this is turned negative. And then that must mean that this is the conjugate acid on this side, or this is the acid on this side, and this would be the conjugate base. So this is the conjugate base. And if we went the other way, this would be the base. So I find my acids, basically the two things with protons that will get removed depending on the direction you're going. And I label them. So the pKa of this one is 25, and the pKa of this one is 15.7. And I just remember it always favors the weaker acid. And the weaker acid is on this side. My student, I always get this wrong. Low, I think it's low to high. So a small number to a large number, it will fly. And then high to low, it won't go. And I always get this backwards because I think of high to low like on the list here. But this means number. So if it's like a large number to a small number in terms of pKa, that reaction won't go forward. So this side of the reaction is favored. So in reality, a better way to draw this would be this way. There might be a little bit of the reverse reaction, but the major products will be, or the thing that will be primarily favored, will actually be the formation of the alkyne and OH minus. That would be a more stable. Oh, I just realized that wasn't focused, probably because I was using this. Okay, so that's question 23. So the left side of the reaction is favored there. Okay, and then 24 is rank the bold-faced hydrogens for the following compounds. So I just do the pK for each one of them. So this one right here, 24, I'll do 1, 2, 3, so that way I don't have to keep holding this up. 4 and 5. So 1, the pKa is, it looks like it's an sp3, it's a hydrogen off of an sp3 hybridized carbon. So that pKa should be about 50. This one looks to be a hydrogen off of an sp2 hybridized carbon, so that should be around 44. This one looks to be a hydrogen off of a nitrogen, but that's positively charged. So that would be similar to NH4 plus rather than NH3. That's the biggest thing students get wrong on these. The pK of NH4 plus is like 9 to 10. So that's really what this will be like. It won't be like NH3, which is closer to 38. 4, the pKa is 25 because it's a hydrogen off of a carbon-carbon triple bond. And then this last one, it looks like it's just an alcohol, and alcohols are usually in the 16 to 18 range. So based on that, what are we ranking? Most acidic to least acidic. So smallest number is most acidic. So I'm going to say 3 with a pK of 9 to 10 is more acidic than 5 with a pK of 16 to 18. Is more acidic than 4, which is 25, than 2, which is 44, and 1, which is 50. So that answer would be, wow, well, actually, this makes your life, you could have, if you were like just not 100% sure and you knew one was positively charged, usually if something's positively charged, it's pretty willing to give up that proton, right? So you could have just gone ahead and eliminated B, C, and E just by knowing that the positively charged one is the most willing to give up a proton. And you would just have A and D left. Now, this is a little tricky because it has the same for, the first two are right for both of these. But then if you just know between an alkene and an alkyne, that's the only thing it switches, which one is more acidic, then you could narrow it down. So you didn't need to know all these pKa's, although it's helpful if you do. You could answer this question even without that. So the right answer for 24 is 3, 5, and then 4. So answer A. Okay. What is the major product of the following reaction sequence? Okay, so again, I see a good leaving group and a good nucleophile. So my first thought here, as this reacts with NaOET, is that OET minus is a strong nucleophile, so it's going to favor the 2 side, and there's heat, so it's going to favor E2. So I'm looking for an E2 reaction. This is pretty narrow, so I think it's going to give me the site F product. So we have a bromine and this CH3. Sorry, just getting situated here. We have a bromine and OET minus. And based on the logic I told you earlier, that's why I think it's going to go for this beta hydrogen. And we don't have to worry about E versus Z because these two are the same. So the stereochemistry doesn't really matter because it'll line up the same either way. There's only one hydrogen it can get, so, and these are both a symmetrical group, so it'll line up that way either way. And then the next step looks like oxymercuration, demercuration, but I want to call attention to this solvent right here. So oxymercuration, demercuration forms the partial positive on the more stable side, so this would attack your one of your OAC bonds would break. I'm always like, I'll do the short version, and then I just do the whole thing. So this is a partial positive that forms just like at the same place that your carbocation would form on the other one, but this is actually donating electron density to prevent rearrangement from occurring. And then your nucleophile, which in this case is CH3O, H will come in and attack and break that bond. So you get OCH3. And this would initially be positively charged and you need to deprotonate it, but I'm going to try to go quickly and not show that step. And then this would be HGOAC, but it gets replaced with hydrogen in the last step. So you should end up with, my drawing is bad, but something along this line as your final answer. And it looks like that's there on answer choice A. Answer choice B didn't account for the methanol being present, so always check for that. Answer choice C, it looks like they did a rearrangement, so they assumed that it went by a carbocation mechanism instead of the bridged ion mechanism, but they had the right nucleophile, and then D did the same thing, but with the wrong nucleophile. So the right answer for that one is answer choice A. Okay, and then for 26, predict the major products. Let's see which that was. The answer choice for 24 was A. And then for 25, the correct answer, also A. All right. So the next question is, predict the major product that forms in trans 1,2-bromomethyl cyclohexane upon treatment with sodium methoxide in methanol in the presence of heat. So I'm going to draw this out so that it's easier to see. Trans 1-bromo 2-methyl cyclohexane upon treatment with sodium methoxide, so that's OCH3 minus, and methanol in the presence of heat. So I see a good leaving group. I see a strong nucleophile. So with those two, I'm going to assume the strong nucleophile favors 2s, either SN2 or E2. And then because it's heat, I think it's going to be E2. So again, I go on that tree where I'm like, if it's strong, it goes for 2. If it's weak or neutral, it goes for 1. And then I break it down even further between SN2, E2. If there's heat or if it's a bulky group, it'll favor this one, secondary or tertiary. And then on this side, primary or secondary. And then also SN2 is favored by more narrow nucleophiles, especially if there's no heat. Okay, so that's how I ended up at E2. So I think it's E2 because it's got the presence of heat there. So this is going to be an elimination reaction. And we had one similar to this on the exam. With E2, you have to consider 2 things, Site-Ceph versus Hoffman. And this would prefer the Site-Ceph product because it's more narrow. And then you also have to consider stereochemistry. So in this case, if it could make either product possible, you would get this for the Hoffman product, and you would get this for the Site-Ceph product if it could make either one, because this is where our leaving group is. So it'll grab a hydrogen from here or here, the nucleophile, and fill in, and the leaving group leave one of these or the other. But before we can commit to one of these or the other, we have to see that it's actually possible. So bromine straight up here. And then on this one, the CH3 is the dash, so that one is going straight down. So that must mean that the hydrogen is equatorial. And that checks out because if we do our wedges all the way around, we know that one wedge will be axial and the next wedge will be equatorial. So there's a hydrogen, an implied hydrogen that's a wedge, so it must be equatorial and it must also be pointing up. So even though the Site-Ceph product would be preferred based on this nucleophile, the Site-Ceph product actually isn't possible based on this nucleophile or based on the substrate because there's not a hydrogen that's anti-periplanar. So this would be the only possible answer. They don't have the stereochemistry showing on here because it's not drawn initially, I think, so that's why. But so the only possible answer would be 2. 1 would be the Site-Ceph product. That's not possible because there's not an anti-periplanar hydrogen there. 2 is the answer choice we got. 3, the bromine would have been right here or right here. So that's too far away. That's like from the gamma hydrogen. And then this one, again, this is too far away. It would have been taken from the gamma hydrogen. The bromine would have had to be attached on the same carbon as the methyl. So that one doesn't work. So the right answer here is answer choice B for 26. Okay. The next one, what functional groups are present in the following molecule? So they say in addition to alkane, cyclohexane skeleton, what other functional groups are present? So I don't really look at these because I get, this wasn't on camera that whole time. So it's asking what other functional groups are present here. I don't look at the lists because that gets me confused. What I do instead is I just identify them. So I see a ketone right here. I see an alkene. I don't know if they're going to ask us about those, but I'll go ahead and write it down. There's a methyl there. I don't think they'll ask about that. An alcohol. And just in case they want to know, this is a tertiary alcohol. And then an alkyne. Those are the functional groups I see, and then I'll go down here and look for that. There's not an ether. Ethers look like this. And I don't see that anywhere. So A is wrong. B, there's not an aldehyde. Aldehydes have a hydrogen here. There's not 2 carbon chains, so can't be aldehyde, so B is wrong. C, I don't see a carboxylic acid. Carboxylic acids look like this. So C is wrong. D looks right to me. There's a ketone. There's an alkene. There's an alcohol, and there's an alkyne. So D is the right answer. Just to check, I'll look at E, amines, NH3 or NH2. I don't see anything like that one, so that one's not right. So the only possible answer choice for 27 is D. And this is a good example of why it's important for students to go through and do the easier questions first, because that would not have taken you as much time as some other ones, and you definitely would have gotten that right. But if you left it for later, you might have missed it. Okay, or I assume you would have gotten it right because you've been talking about functional groups for so long now. Question 28. What are the major products formed when trans 1-bromo-2-methyl cyclohexane reacts with sodium isopropoxide and isopropanol? So I'm going to draw this back out again. 1-bromo-2-methyl. 1-bromo, and I think it was trans, 2-methyl. Reacts with sodium isopropoxide. So I see a good leaving group on a strong nucleophile. The isopropanol is probably just the solvent. So I think when I look at this, it's going to favor 2. There's no heat, but this is relatively bulky, so I'm actually going to think it's going to favor E2. And then I'll just double check, to see what the options are. So I think it could favor SN2 or E2. I just want to say that because this is strong. It could favor SN2 or E2. And it's kind of hard in this case. I think it's borderline. It really could do either one of these, I think, because this isn't as bulky as like a terbutoxide, but it's not really narrow either. So the bulkiness of this is going to make me think the bulkiness of this, with this being secondary right next to a tertiary, that's going to make me think the sterics favor this going for E2 over SN2. But it's kind of tricky. You can definitely be sure it's it's going to be 2, but you have to decide if it's SN2 or E2 based on these factors. And for me, this being bulky-ish, this being secondary right next to a tertiary, that makes me think it's sterically hindered, and the E2 product's going to be favored. Also, because this is bulky, I think it's going to favor, or bulkier, I think it's going to favor the Hoffman product. And because I am pretty sure there's not an anti-periplanar hydrogen on that one, because it's very similar to one we just did, where the bromine's up. Oh, no. Yeah, CH3 is pointing down, and the hydrogen's here. So this is the only possible product. If you can't tell, I'm trying to drive that home. So the answer choice there would be answer to choice 2. So 1 and 2 would be if it could get a site F in a Hoffman, but 1's not possible because there's not an anti-periplanar hydrogen. And 3 and 4 would be if there was a substitution reaction. I don't think it's going to favor a substitution reaction because it is so bulky. But if there was a substitution reaction also, it would have to be an SN2 reaction. And if it started out as trans, then it would end up cis. So the only one that it could be would be 3. But I don't think that would happen because I don't think that with the bulkiness of this group and this group right next to it, that would be very energetically favored. So I would go with answer choice B. I hope this is helpful to you, that you've kind of been able to see like my thought process. That this is literally, I haven't worked these practice problems before. I pulled them for you from like a bank that I thought would be useful, but I haven't seen them before. So I really did this in a way to try to help you see how I literally approach practice problems so that you kind of get that practice. Okay, this question is explain in your own words why cyclohexanol is more basic than phenol. In my own words, I'm going to say resonance. So because if you just put resonance, I wouldn't give you that. I've been working on causal relationships with you all. So this is phenol and this is cyclohexanol. If both of these lost their hydrogens, their protons, this negative charge is focused on the oxygen atom, but this one is able to be distributed around the ring due to resonance. And because of that, oh wait, no, I drew this arrow wrong. Because of that, the negative charge is actually distributed all the way around the ring instead of focusing on one spot, which makes it more stable. So because resonance is able to stabilize the lone pair left behind, or the conjugate base, the phenol is more willing to give up a proton than cyclohexanol, which would bear the brunt of the negative charge all on one atom, and it wouldn't be able to distribute it. Okay, so that would be how I would answer that question. The next question is, what would be the product of the following reaction? I don't know if you can see that very well. It's just a cyclohexane ring, and you can see my ring light. It's like circling the question we're going over. That's funny. So this is 30. We have just a solvent, CH3OH, and nothing else. So I see a good leaving group in the bromine and a weak nucleophile. I think this is going to be solvolysis, where SN1 occurs with the solvent as the nucleophile. Because it's weak, it's going to be 1. Whether it's SN1 or E1 depends really on heat and bulkiness. This is not bulky, and it doesn't talk at all about heat, so I'm going to go for SN1 on this because of that logic. So the first step in either one of those, actually, it doesn't matter, is the leaving group leaves and leaves behind a positive charge. And then whenever you see a carbocation, I want a red flag to go off in your mind that rearrangement will happen, so it will actually trade place with the hydrogen right here. And notice I don't draw my wedge or dash anymore because this is sp2 hybridized. And then your nucleophile will attack right there. OCH3, and it'd be H, this oxygen would be positively charged initially. And then you'd add base or the solvent in the solution, whatever, would deprotonate it, and you'd get OCH3, and you'd also get the enantiomer. So the right answer for that one is, let's look. A looks like it doesn't undergo rearrangement. B looks right, but it doesn't mention the enantiomer. C is the enantiomer, so I guess that would make E the right choice. And this is kind of a hint. You can't get a racemic mixture of A and B because they are diastereomers, not enantiomers. Okay. Next question, question 31. Give the formal charge of nitrogen for the following structures. I think this will be a lot easier for you when you had similar questions on the first exam. So here there's 4 things bonded to nitrogen. So I would say that would be positive because nitrogen starts with a formal charge of 5 minus 4 bonds, no electrons, equals positive 1. For 2, that nitrogen starts with 5 valence electrons. And again, if you don't know where this comes from, you can check the the periodic table in the column. It will have the numbers above. That's how we can tell how many valence electrons are there. So 5 is what it comes with, and then there's 2 bonds and 4 electrons, minus dots, minus lines, right? So 5 minus 2 is 3, minus 4, so that's negative 1. 3, there's 5 things that it starts with, 2 electrons and 3 bonds, so this one's neutral. 4 looks like it has, starts with 5, There's one bond and then two bonds that aren't specifically drawn in. That's kind of sneaky, to hydrogen plus 2 electrons, so that's 0. And then same thing with 5. It has, structure 5 has 5 valence electrons, 3 bonds, and 2 lone pairs, so 0 again. So this one's positive, this one's negative, and these 3 are neutral. Okay. The carbon-carbon bond in the following molecule results from the overlap in which orbitals in the order C2, C3. Okay, so we're looking here and here, and basically what this saying is, what is the hybridization of each of these carbons that's going to be overlapping to form the bond? And this has 2 implied hydrogens here on carbon 2, so I'll draw this out for you. We don't really care about what's going on over here, but there's 2 implied hydrogens here. So there's 4 things bonded, so it must have 4 orbitals. So that must be a hybrid of 1s and 3 p's. So this is sp3 hybridized at carbon 2. Carbon 3 has 1, 2, 3 sigma bonds. It does not have this. This is made up of a pi bond. It's an extra lone pair, right? So we're not counting that as we're trying to check the hybridization. We're only looking for sigma bonds. So C3 must have 3 orbitals making up its sigma bond. So that's 1s and 2p. So this is sp2 hybridized. So the bond between these is made up of the overlap of these orbitals. So it must be sp2, sp3. Oh wait, but it says in that order. So I think it's sp3, sp2, carbon 2, and then carbon 3. So sp2 first, or I'm sorry, sp3 first for carbon 2, and sp2 for carbon 3. So that's all I'm looking for here, is that hybridization, and it looks like sp3, sp2 is answer D for question 32. Okay, 33, which compound would you expect to have the highest boiling point? That's going to be the one with the best intermolecular forces. And the best intermolecular forces, if there's a hydrogen available for hydrogen bonding, which is not a real bond, and I hate that name. So that's going to be a hydrogen bonded to oxygen, fluorine, or nitrogen, because it makes so much of a strong dipole that it's so partially positive that the bonds, intermolecular forces that hold it together, act a lot like bonds. And that's why they call it hydrogen bonding, basically, in a nutshell. So I'm going to look for the one with hydrogen bonding, and I can see right away that C and D have alcohol groups, a hydrogen bonded to an oxygen. So these 2 would be the top candidates, and between those, C has 2 OHs, so 2 hydrogens available for intermolecular forces with hydrogen bonding, and D only has 1. So I'm going to go for answer choice C on that one. Markovnikov addition of HI to 2-methyl-2-butene involves, okay, so let's draw out 2-methyl-2-butene, 1, 2, 3, 4, 2-butene, 2-methyl, 1, 2, 3, 4, 2-methyl-2-butene. Is that right? Yep, okay. 2-methyl-2-butene, and we're doing HI, and it's not in peroxide, it's anti-Markovnikov. It goes anti-Markovnikov, sorry. It goes Markovnikov. I just said the same wrong thing like 3 times. I'm losing my ability to speak. Okay, so the hydrogen will add to the side that's less substituted so that the carbocation can be on the side that's more substituted. And then I minus will attack right there. And that will be, that's your overall mechanism. So the question is, what does it involve? Initial attack by the iodide ion. I would say no. The iodide ion doesn't attack. The initial attack that we drew out happened from the alkene, right? So that's not right. Oh, so the next option, B, initial attack by the alkene, seems like it's the right option. So I'm tentatively going to say that the answer for that one is B, but I'm going to read the rest of them just in case. Isomerization. We don't ever see isomerization in addition reactions. Like, how would that even work? So I don't think that makes sense. Formation of a iodonium ion. So that'd be like bromonium ion or chloronium ion or mercurinium ion. But that would be if you added I2, right? But this is the Markov-Nikov addition of HI. It's acid catalyzed, right? So it forms a carbocation. It doesn't make the bridged ion. Rearrangement is possible. It's just like adding acid catalyzed water across a double bond. So I would say that one's not a good answer choice. That would only work if we were adding I2 to that and forming that bridged ion. And the very last one, forming a carbocation at C3 doesn't super make sense because the carbocation is going to form at the most substituted position, and that's carbon 2. So I'm going to stick with my initial answer of B. What would be the product of reacting the following molecule with sodium ethoxide? Okay, well, I see a good leaving group and a strong nucleophile. So basically, I'm going to say this is going to be a 2 reaction, either SN2 or E2, because it's a strong nucleophile. And there's no heat to tell me right off the bat which way it's going to go. But this is a tertiary leaving group, and tertiary leaving groups don't go for SN2 reactions almost ever. So based on that alone, I'm going to say it favors the E2. If you can think about the chart I've made all the way back in the day, it looked like, I guess it looked similar to, I feel like I drew it out somewhere in here, like this, but I drew it all the way out. Primary and secondary is on SN2, secondary and tertiary is on E2. So this being a tertiary really makes me think it goes for E2. It could do Zaitsev or Hoffman product theoretically, but because it's more narrow, I think it's going to be the more substituted. So it could technically steal from, I guess I should have drawn this out. We always have to consider all the different options it could do. So it could also take this one and kick the leaving group out that way. So you could have either of these products. This is the Zaitsev, and this is the Hoffman, but because it's more narrow, it's going to go Zaitsev. There are 2 hydrogens here, so it would have been able to line up with one in the plane of the page, so I'm not worried about the stereochemistry. So that would be my answer for that one, for 35. And I asked you to justify your answer, so I was hoping you would be able to explain all of that out. Okay, so the next question, which reagents would you use in the given reaction to form the desired product? Okay, so I look at this and I see that we started with a double bond and we ended with an alcohol. So the first thing I think is addition of water. So we have 3 options for addition of water: acid catalyzed, oxymercuration, demercuration, or hydroboration oxidation. Okay, these are our 3. That's my shorthand for it. This is going to have rearrangement. This will be Markov-Nikov without rearrangement, and this will be anti-Markov-Nikov. So I'm going to look and see where the alcohol would have added for Markov-Nikov without rearrangement. HGOC, the alcohol would have gone here. For hydroboration oxidation, it would have gone here. But it looks like this methyl group moved over here. So that tells me this is an acid catalyzed addition of water. So the only answer choice it could possibly be would be answer choice D. Now, if you really want to push yourself on this, you can, I would recommend you go through every single one of these and predict what the products is. So I'll do that quickly. If you react, because you should know all these before the exam. If you react ozone, the methyl sulfide is just the solvent for that. If you react ozone, it'll split it in half, and it'll have an aldehyde on this side and a formaldehyde on the other. Oxymercuration, demercuration would have added the alcohol on this side, and there would have been no rearrangement. BH3THF would have added the alcohol on this side. H2SO4 we did, that gives you this product. And then KMNO4 cold would give you a syn diol. So it would be a diol on each side of the double bond. Okay, 37, which reaction would yield a meso compound? So I got a bunch of questions about this, and I actually hadn't worked it out yet, and I'm kind of glad that I hadn't when I got those questions because it forced y'all to work it out. So here's what I'm going to do. I'm going to draw out cis-butene. I'm going to draw out trans-butene, cis-butene, and cis-butene. And I'm going to give you the products of each one of these additions and then tell you which one I think would yield the meso compound. And I would need to add it to change it to a Fischer to be able to do that. So osmium oxide adds alcohol syn like this. Dilute KMNO4 actually also adds alcohol syn. So 2 wedges. H2 and palladium, that's just going to get rid of it and turn it into an alkane. Just gets rid of the double bond. And then the last one, Br2CCl4, it's going to add, it's cis. It's going to add 1 bromine as a wedge and 1 bromine as a dash. Okay, so that's what we have. I'm going to draw these in Fischer projections. So this one actually is already sort of in the Fischer projection form. So say I'm floating above it and looking down. The OHs are on my left, the hydrogens are on my right, and the CH3 looks like this. So it looks to me like this is a meso compound. But I think, well, none of these is. I thought more than one of these was also an answer choice, but it's not. Okay, so I'm going to switch this to be in the easier to visualize meso form, where if this alcohol is pointing towards me and pointing down and I rotate it, the alcohol is now pointing backwards. So the alcohol is over here and the hydrogen becomes on a wedge. So I'm going to put the, I'm still on this side looking at it from above. So the alcohol is on the left, the hydrogen is on the right, CH3 going straight back for both of these. And then on the bottom one, the alcohol is on the right and the hydrogen on the left. So that is not a meso compound because the CH3s are already lined up, but the rest of it isn't. So this is not a meso compound. This isn't a meso compound because it has no chiral centers. So the only other one it could possibly be would be this bottom one. What is this? E? No, D. Oh, I don't have letters on there. My bad. So it's already in the Fischer projection form, so that makes my life easy. There's a bromine over here and a bromine over here and 2 hydrogens, if I was looking at it from above. So this is not a meso compound either. So this answer, answer choice A, is what it would have been, is going to be the one that yields a meso compound. So I had a lot of questions on that. So you have to be comfortable knowing that it starts with cis or trans, knowing if they add wedges or dashes, and then also being able to convert that into a Fischer projection or see if it has, the thing that you're looking for. Okay, which reagents would you use in the given reaction to get the desired products? My ring light's kind of reflecting weird, but actually this looks very familiar to the one we had before. It looks like a double bond split this right here. And one side made a formaldehyde and one side made an aldehyde. So if you did what I encourage you to do up here and predicted what all the products would give you, then you'd have the answer, which to number 38, which would be ozone. So O3, and then you can have dimethyl sulfide or something like that as your solvent. I just am looking for you to know that it's ozone. Okay. Which reagents would you use to generate the following transformation? So again, this is asking you to look at what's changed. So, and what would you use to change that? So it looks like we've changed this alcohol to a BR, and we talked very briefly in class, but you are responsible for knowing this on your final exam, that you can convert an alcohol to a bromine by using PBr3. You can also use SOCl2 to convert an alcohol to a chlorine. So yeah, that's what I would use. Somebody asked me if you could use HBr because it would attack, but this would protonate to make water. Then the leaving group would leave, and then the Br minus would come in, the leaving group would leave, you'd get a carbocation, and it would rearrange. So then the Br minus would come in and attack here, and we don't see a rearrangement occurring. It doesn't represent rearrangement happening here, so oopsie. So I'm going to say I would not expect HBr to actually work. I think you get too much of the rearranged product. Okay. Sorry, my computer's dying. The next one, what would be the major product of the reaction shown? Okay, so the first thing, you replace the OH with the leaving group. So, this first reaction, sorry, I don't know where my brain is at. I was drawing this out anyway. This first reaction is, hopefully you recognize this as a meso group, and it converts alcohols into good leaving groups. So it will turn my alcohol into a good leaving group. I can't remember off the top of my head if it inverts the stereochemistry or not. So let me check real quick. Okay, I did a quick Google search, and I'm pretty sure, I don't have my textbook with me, but I'm pretty sure it does not invert the stereochemistry here. It doesn't change the stereochemistry, and so I just scratch that out, usually, and write leaving group on it, actually, so that I know that it's a good leaving group, and that's basically all it does. So the mesylate form is basically just converting this alcohol to a good leaving group. And then you have NaI and ethanol. So I'm seeing I minus and a good leaving group. So this is either going to be a substitution or elimination reaction. But as I would actually say it's more likely to be, it's a minus, so it's SN2 or E2. I would think it would be more likely to be an elimination reaction because it's right next to this hindered group, but there's not an elimination answer choice as an option. So then it must be a substitution reaction in SN2. And I think it's really just testing you to see if you know that the SN2 inverts the stereochemistry and that the mesylation doesn't. So the right answer for this one, and also that this one down here, the stereochemistry doesn't change. So the right answer for this one should be, let's see, the one where the I is the dash. So I think, and the CH3 stays as a wedge. So I think answer choice 2 is correct. You would not get any equimolar mixtures happening because it's not an SN1 mechanism. It has to be SN2 because it's negative. So the answer is answer choice B. Okay, 41, what would be the major product of the following reaction sequence? So this first step, it might be difficult on the first step to know if it's an addition reaction or if it's a radical reaction. Those are kind of the only two times we've seen Br2, but because there's light present and there's no alkene to add it to anyway, the first step I'm going to say is going to be a bromination reaction, so or the radical reaction. So this is a structure we have. The initiation step will take place, then propagation will take place. You'll get your radical right here. So I'm not going to go through that whole reaction mechanism, mostly because it's late and I'm trying to wrap this up for y'all, and I've gone over that mechanism a few times already. And then the next step, there is now a good leaving group because we've added a bromine, and it's a good leaving group on a tertiary carbon. And then this is a weak nucleophile. There's no heat and it's not super bulky. So if it's a weak nucleophile, it goes towards 1, and there's no factors that make it favor E1 over SN1. So I think this is actually going to be an SN1. So the leaving group will leave, and you'll get a carbocation, and then this CH3, CH2OH will come in and attack, and you'll end up with, this would initially be protonated, but you'd get a deprotonation step, and so your final answer would be answer choice C. So this kind of shows you how these reactions build on themselves, how you can take an alkane and make it functional and then react it with something else. I don't know what happened with the numbers here, but 41 skips down straight to 53. So 53, the answer of which radical would be the least stable. Primary radicals are the least stable, but they can be stabilized by resonance. So these secondary are more stable than these primary, except this is stabilized by resonance. So this actually would have an advantage because it's at the allylic position. So this would actually be more stable than B here. So I'd actually rank A as the first most stable because it's a secondary allylic. C is the second most stable because it's a primary allylic. And then B and D would be less stable than both of those, but D would be even the least stable because it's on a primary, whereas B at least is secondary. So 53, the answer I would go with would be D. 54, what is the expected product of the reaction shown? So again, we've had a lot of bromine show up, so this could be an addition reaction or this could be a radical reaction, but it's not in the presence of heat or light, it's actually in the presence of water. So my thought is that this is going to be a halohydrin formation. And my other thought is you need to know if it's Markovnikov or anti-Markovnikov because it's asymmetrical. So this alkene attacks, and actually the bond breaks with the bromine, and a partial carbocation forms as the bromine goes to the other side and lends some of its electron density over there, making the bromine partially positive as well, but keeping this from rearranging or doing anything else. And then your water will come and attack and you will have OH2 plus and bromine over here, and then that will get deprotonated. You can add base in there and it'll take that away, or you could do something else. The solvent, I don't really care a ton about where that comes from, but so you'd have OH and Br, and this adds anti, so you'd get a wedge and a dash. And notice I added the stereochemistry in on the other one as well. You'd get that plus the enantiomer, because the flat bromonium ion can be attacked from either side. So you usually get anti-addition, but you get the enantiomer as well. So that would be the product I expect. Describe in your own words the process for identifying primary, secondary, and tertiary alcohols, amines, and halogens. So alcohols and halogens are different than amines. So you look for both alcohols and halogens, you look at the carbon it's directly attached to, and then how many carbons is that bonded to. So in this case, 1, so this is primary. In this case, it's bonded to 1, 2, so secondary. Amines, this would be a tertiary amine. You look at how many things are bonded to the nitrogen itself. So if this is 2 hydrogens with 1 CH3, this would be primary. So make sure you know the difference between those because students will often get this wrong on their final. Okay, now if you had CH3 with HBr and peroxides, so I'm initially going to draw, it's just easier for me to think of everything in terms of the initial acid catalyzed addition for whatever reason. I guess carbocations just kind of makes sense to me. So if this was not in peroxide, you would get this product where you get a carbocation and the bromine comes and attacks. And there's no rearrangement in this case because it's already tertiary, so it's perfectly happy. But if it were in the presence of peroxides, you don't have to memorize the reaction mechanism for this, but it just flips around where actually the bromine adds first and then a radical is formed right there, and then a hydrogen adds on right there. So this would be the product you would get in the presence of peroxide, and this would be the product not in the presence of peroxide. So this is anti-Markovnikov, and this is Markovnikov. And I believe that answers the next question as well. The stereochemistry on this is that it would give you a racemic mixture because it's a radical reaction. And radicals can attack from either side. Okay, so for 56, the answer was the anti-Markovnikov one. And for 57, you could achieve this by doing HBr not in the presence of peroxides. And that's it. We did it. So all of the questions have been covered in this video or the one before. So hopefully that was helpful to you and that this was a good review for you going into your final. And I will see you all hopefully tomorrow.